Markovich, who is a local almost. And he's in Karls now. We'll talk about price formation of which gives right to certain free boundaries. I guess we at least might use it to not lose money. I don't know, winning money. Please.
Well, thank you, Henrik. Thanks to the organizers, of course, for having me here. It's a pleasure to be back in rainy England, although it's not rainy today, it was yesterday. Okay, so let me start out by saying that this is joint work with a few colleagues, and that is Martin Burger from the University of Münster in Germany, and Luis Caffarelli from UT Austin, and Marie-Therese Wolfram from the University of Vienna. Okay, so this is more or less an overview of what I'm going to tell you in the next 45 minutes. First of all, I'm going to introduce a price formation model which was written down for the first time maybe 7 or 8 years ago by Pierre-Louis Lyons and Jean-Michel Lazeri, in a really seminal paper in which they introduced mean field games. And they, in that paper, they had like a list of examples of mean field games, and one of them was exactly the boundary value problem that I'm going to discuss. Yeah, I'm going to speak about some structural features of that model, and then in particular I want to address one issue, and that is Lazeri and Lyons, they have just written down the equations, and they basically said that's it, that's the model, right? And well, I mean, there is some, as you shall see, there is some internal logics to it, but we were sort of after a more coherent modeling approach, or should I say a more microscopic modeling approach. So since we come from kinetic theory, an immediate idea for us to go more microscopic, or actually mesoscopic in that sense, was to start from a Boltzmann-type description of an economic market, and then sort of see how we can get from the mesoscopic model to the macroscopic one by techniques which are very well known in kinetic theory. So actually I shall be discussing various limits of the Boltzmann-type model, and actually it turns out that in one of those limits, which is the limit of large trading volume, actually our Boltzmann model really converges to the Lazeri-Lyons free boundary problem, and there is actually quite a few mathematical intricacies in this that I'd like to point out to you. Yeah, and then in the end I'm going to speak about numerical simulations, time permitting, if Henrik doesn't flag his 2-minute thing too often. Okay, now here is the setup for the market. So what we do is we consider a market for one economical good, in which you have a large number of buyers and a large number of vendors. And the basic assumption comes here. The basic assumption is that we assume that each agent who has just bought the good for the price X, he wants to resell immediately, but he wants to resell for at least the price X plus A, because he has to pay a fixed transaction cost A. So think of this. In every transaction that is done in the market, a fixed amount of money, that is A, has to be paid. Okay, so that means if you buy at X, you want to resell at least at X plus A. Okay? The other way around, an agent who has sold the good for the price X, he wants to rebuy immediately. Okay? And of course he wants to rebuy immediately for a price which is at most X minus A, because also he has to pay the transaction fee. Okay? Now the mathematical description works in the following way. We denote by F as a function of X and time t, where X is the price, the density of buyers at time t over price. And we denote by G the density of vendors at time t. And the model that Lazeri-Lyons wrote down is, as you shall see in a moment, is a free boundary value problem for the functions f and g. Now here there's one thing that I should mention immediately. This is not a realistic model for an economic market. As you shall see, there is a lot of modeling shortcomings to it. Okay, but I'd like to show you that there is some very interesting mathematics to it, and that actually I do believe that if you go on thinking about modeling deeper in an economical sense, and actually you can use this as a basis for further activities. Okay, so here's the model which Lazare and Lyons wrote down. So think of f, the density of buyers, as a function which lives to the left of the agreed market price P of t. And P of t is actually an unknown of the model. Okay, it's actually the free boundary. So think of f being positive to the left of P of t, and think of f being 0 to the right of P of t. Okay? Then to the left of P of t, f is assumed to satisfy this heat type equation. So let's just look at it for a moment. So on the left-hand side, you have just basic heat flow. So this essentially means that the market has some randomness in it, right? Which is described by, actually I should put the sigma square half up front here, but let me scale it to 1. And the right-hand side, well, the right-hand side is interesting. It's a delta kick. And if you look at it, you see that the delta kick happens when the price x reaches the agreed price minus transaction rate. So you can think of sort of, this is the price where the buyer gets interested. Okay? And then there is a strength of the delta kick, which is this function lambda of t, which I shall discuss in a moment. Okay, now the density of vendors G lives to the right of the agreed price P of t, and is 0 to the left of the agreed price P of t, of the agreed price P of t, and to the right it satisfies a very similar heat type equation. So again, you have heat flow, then you have a delta kick, you have the same strength lambda of t of the delta kick, but the delta kick now happens at a different location. It happens at price x equal agreed price plus a. This is where the vendors become interested. Okay. Now the only other quantity that I have to discuss is lambda of t. So think of lambda of t as sort of the flux, okay, or the transaction counter. Okay. Then lambda of t is just given by the derivative of g at p of t, which is equal to which has to be equal to the negative derivative of f at p of t, and I'm going to argue in a moment why that has to be the case. Okay. So yeah, then of course we need a free boundary condition, and the free boundary condition which should determine p of t is simply f of p of t at time t is 0 and g of p of t at time t equals 0. So think of it in the following way. Think of it, here is your price axis. So here I plot f and g, and I'm at a fixed time t. Assume that at the fixed time t, here is my agreed price, then f lives to the left, and g lives to the right. Okay, and these derivatives are the same in absolute value. Okay, so that's the model as Lazare and Lyons wrote it down. They did not really motivate the model. Well, they said, yeah, it comes from mean field game theory. That was it. I asked Pierre Louis about it, and he said, don't really remember, but it's for sure is on my videos of the lectures at Collège de France. So when you go down to his videos, you find the video screen maybe this big on your computer. You have a scrolling tab which is this long, covers about 38 hours of lecture. So it takes a pretty refined touch of your hand to find the spot. I didn't actually. Okay. So this is the model. And yeah, so here is the first simplification, which was already given by Lazare and Lyons. Let me introduce the signed density of buyers and vendors. So this is just f to the left and minus g to the right. So I flip this function over. Okay? And then I can subtract the two equations, and what comes up is just one equation for the difference. Okay? Which is v. So I have this one parabolic equation. The free boundary condition for p of t now reduces to v of p of t, and t is 0. And lambda of t again is given by the derivative at the free boundary. Okay? So that's maybe a simplification. Yeah, I should maybe say one thing about the lambda of t. Now what I said is that when you're in the market and you buy, you want to resell immediately afterwards, and when you sell, you want to rebuy immediately afterwards. So that means in every transaction event, there is one seller and one buyer incoming, and there will be one seller and one buyer outcoming. They will just exchange their tags, if you want. Yeah? But that means that you will have the conservation of the total number of buyers, and you will have the conservation of the total number of vendors. And this is precisely where the definition of lambda of t comes from. You take this equation, you integrate from minus infinity to p of t, you find an expression for lambda. You take the equation again, integrate from p of t to plus infinity, you find the same expression for lambda. Okay? All right. So this is the model. Well, there have been quite a few papers on this, yeah, there's been papers by Gonzalez, Gueldani, by Lincoln Chase, Gueldani, Gonzalez and Kim, and then we were also in the game. And somehow all those papers didn't really get it right. And what do I mean by not get it right? What I mean is the big problem here is to prove a global existence theorem for this free boundary problem. And this is an interesting experience because when you look at the problem, let me show it to you again. Now you're tempted to say, well, this is a 1D thing. It's a 1D heat equation plus some deltas on the right-hand side. I can almost walk over this, right? And then you grind, and you're still in the process of walking over it and don't get anywhere. And yeah, somehow everything that we tried from free boundaries, from Harnack to I don't know what, just failed. And what's the issue? The issue is that you need, in order to get the global theorem, what you need to prove is that the free boundary remains continuous at every bounded time interval. And that's precisely what is the problem. So it's not even C1 or anything like that, or C01, it's just continuous. Still, I mean, all you need is some control on the modulus of continuity. Still, it didn't work. Okay, so here is an idea, and here's actually what we did a few years ago. Think of, now this is time and this is price. Okay, so think of, assume that you have a solution and this is your free boundary, P of t. So what is important for the problem is those parallel curves, P of t plus a and P of t minus a, and those curves here. And what happens at those curves? Well, if you fix a time t, and if you plot the solution, V of t, what you find is that, of course, it's smooth through the free boundary, but you have a kink at P of t minus a and at P of t plus a. Okay? And the kink is determined by the size of lambda of t. So the jump in the first derivative is determined by the size of lambda of t. And what is lambda of t? Lambda of t is just the negative of this derivative. Okay? So what does this tell you? This tells you something very simple. It tells you, well, look at the solution. Yeah, look at the positive part of the solution. Okay? So this angle here is just a negative of this angle, correct? So shift the positive part by a to the left and add this shifted positive part to the positive part of the solution. So what happens is the kink that you get originally at a, or at P of t minus a, is eliminated, but it is moved to P of t minus 2a. Correct? So you just keep doing this. Do it a few times. Do it many times, and then you will keep shifting the singularity out to minus infinity. Okay, now of course you can do the same thing on the right-hand side with a negative part, and then what happens is if you define this transformation, so you take a solution of Las-Reliance, okay, take the positive part, consider the sum of the shifts, take the negative part, consider the sum of the shifts to the other side, then what you find is that this function capital V will satisfy the heat equation because you have shifted those singularities out to minus infinity and plus infinity respectively. Okay? Well, it will satisfy the heat equation with a particular initial datum which you compute from the transformation of the initial datum of the original problem. And the important issue comes now. The important issue is that the free boundary P of t, okay, which was the zero level set of the function small v, is still the zero level set of the solution of the heat equation capital V. Okay, because locally at the free boundary, the transformation doesn't modify the function. Okay. Now, of course, I mean, this tells you that if you have a solution of Lazare-Lyons, you can pass to heat. In reality, what you want to do is exactly the other way around. You want to start with a solution from heat, and you want to prove that this is a solution of Lazare-Lyons. And actually, this works as well. This is the back transformation. And what you need is basically to prove that this is positive and this is negative, but that's just a comparison principle on the heat equation based on the particular structure of the initial data.
So what you mean is that for each n there is one solution on the right and left with the same heat.
Sorry, what I mean is for each
n, so there is one function when you define it like this from right and left when you shift it, and then the heat will be the Dirac mass with plus and minus sign, and they cancel each other?
Yeah, exactly. I mean, yeah, exactly. You see, I mean, look at it geometrically. Yeah, the derivative is just gives you this angle here, correct? This is lambda of t, which is the size of the delta kick. Okay, and this is precisely the same thing as here. So you just add the negative and the positive, and you get 0. It's really too simple. It took a while. Okay, so here's the theorem, the global existence theorem, which says that there exists a unique solution V of the Lazare-Lyons free boundary problem, but this is global, and the free boundary is continuous, and once it's continuous, it's everything you want. Okay, so here's a sketch of the proof. The first thing that you have to show is that that the free boundary cannot turn back. That's a maximum principle argument. There's a theorem which says that the number of components of the solution of the heat equation does not increase in time. This is the harder, I mean, this was actually the hard part to exclude when we worked on the original problem without the transformation that I've shown you. You have to show that, as I said, you need to control the modulus of continuity, so basically you need to avoid oscillations in finite time. Now here it's simple, because capital V satisfies the heat equation, and the solution of the heat equation is analytic in x for every time t. So this cannot happen, because if it happened, the solution would have to be 0 on this whole interval. Dead. There is another thing that you have to show. You have to prove that the free boundary cannot walk off to plus or minus infinity in finite time. But that's actually quite simple. That works by using the structure of the initial data through the transformation that I've shown you. So basically, through what the transformation does is it keeps moving mass outward. Okay? So basically what you prove is that there is always a unique point x, for every time t there's a unique point x, such that v is 0. Okay? So that cannot happen. Okay, so this sort of kills the problem. Yeah, there's something else we did. You can use this to find something to get information which the economists are interested in, and that is what happens as time t converges to infinity. Will the price stabilize? And actually what we proved is that yes and no, and the yes is if the mass is on the left-hand side, if the number of buyers is equal to the number of vendors, and no if they're different. Okay, but still there is some fundamental issues in this model that, the modeling of it is not really clear. It has some intuitive, you sort of understand it intuitively, but in the way that Lazare-Lyons wrote it down, it's very hard to sort of pinpoint the modeling structure of it. So here's our idea. Now this comes sort of from gas dynamics. So what did Boltzmann do? In gas dynamics, he said that, well, basically motion of gases is sort of controlled by the collisions of atoms or molecules. And what you need to do in order to understand the macroscopic behavior through some kind of thermodynamic limit process is that you have to understand what happens in each individual collision event. And of course, in gas dynamics, you have physics on your side, you have conservation of momentum, and you have conservation of energy, and that essentially defines the collision law. And then you write down the Boltzmann equation. So basically, we thought, well, why not apply the same thing here, go back to kinetic modeling, but of course, the collision events, that is when a buyer and the vendor meet, and when they do their trading, of course, has to be adjusted to the situation at hand. So the basic, I mean, when you do kinetic theory, the basic quantity that you have to determine through modeling is the so-called collision kernel. And the collision kernel here is a function of 4 scalar quantities, that is x, y, x prime, and y prime. And you have to think of this number here as a counter for the trading events per unit time of the buyers who are willing to buy at price x and resell afterwards at price x prime, and the vendors willing to sell at price y and rebuy afterwards at price y prime. So if I know that function, okay, that collision kernel, I can use basic kinetic modeling, and I can write down a kinetic system for f and g. Now, here's maybe a slight kinetic cheat. We added diffusion in both equations, in the equation for the buyers and in the equation for the vendors. But that goes with the spirit of market theory. Now, here is the kinetic modeling. Typically in kinetic theory, what you have is you have to count the incoming collisions and you have to count the outgoing collisions, and you basically have to subtract them. Okay, so here is the counter in the density of buyers. Here's the counter for the incoming collisions, and here is the counter for the outgoing ones. And all this is based on the fact that the collisions are binary. So it's always one buyer and one vendor that meet. This explains the product of f and g. Okay. Now here is the analogous equation for the density of vendors. Again, you count the incoming collisions, you subtract the outgoing collisions, and all this is essentially done through an appropriate permutation of these variables here. It's just it's bookkeeping. It's really nothing else but bookkeeping, who buys and who sells. Okay, now what does that mean? If I want to come up with something sensible, I have to model k. Okay, so here's a simple way of modeling k. Let me assume, first of all, that somebody who buys at the price x will not resell for a price larger than x plus a. He will resell exactly for x plus a, and the same on the vendor side. So that means in the collision kernel I have these deltas in here, okay, which do precisely that job. And now I need to model this remaining function k0, and what I do is I assume that the bids of buyers and vendors are always matched exactly. So that means that k0 is just a factor, k, multiplied by delta of x minus y. And this, if you think of this number k, this is just a trading rate. So it's a counter for the trading events. Yeah? Okay. All right. Now, just plug in this expression into here, plug in this expression into the equations, and evaluate, and what you find is a system of 2 parabolic equations, nonlinear parabolic equations with shifts. Okay? Now keep in mind here one thing. In Lazare-Lyons, f and g, f live to the left of the free boundary and g live to the right of the free boundary. Here in this model, f and g are globally supported. And technically speaking, there is no free boundary. Okay? So, I mean, both of these equations live on the whole real line. Okay? Now, clearly you have conservation of the total number of buyers, and you have conservation of the total number of vendors. This is obviously built in the modeling process. Okay, now, how do you go about analyzing this? There's an interesting thing about this, and that is there is 2 heat equations behind that model. That's the following. Let me define this. You can think of it as a Neumann series, actually. So here I sum the shifts to the left of the density of buyers, and here I sum the shifts to the right of the density of vendors. Okay? And then you take the difference of this, call this capital phi. And what you find is that this function capital phi satisfies a heat equation. Okay? Similarly, by immediate verification, you find that f plus this shift of g also satisfies the heat equation. And it turns out that those 2 heat equations, well, which are the same heat equations, of course, but different initial data, they sort of give an inroad to the analysis of the problem. Now the question that comes up, of course, is how is this connected to the Lazare-Lyons model? Now think of Lazare-Lyons. Here it is. Now, if you think of the Boltzmann model that I've just shown you, again, take the difference of f minus g. Contrary to Lazare-Lyons, you don't get a closed system now, but you get something, whoops, sorry. Where am I? Okay. Okay, but what you get is something that looks like this. Now the interesting thing is, I mean, this first function here clearly is a function of x plus a. This is also a function of x plus a. This is a function of x minus a. This is also a function of x minus a. So this is the idea. The idea is to consider the limit as the large as the number of trading events, or as the number of transactions, k tends to infinity in this Boltzmann-type model. And what we want to show is that as k tends to infinity, we come up with precisely the Lazare-Lyons problem. And that would sort of, I mean, that would sort of explain modeling more from a more mesoscopic principle than what Lazare-Lyons did. Now, here is the main idea of the proof. Well, the first thing that you prove is that the product of f times g converges to 0. Okay, and that's actually a very simple exercise. Take this equation, divide by k, assume that you have bounds on f and g, which you get from the heat equations, and what you find is that f times g is a 2a periodic function in the limit. Now, the only 2a periodic function in L1, say, is of course the 0 function. So f times g in the limit has to be 0. Well, the next step is that you prove strong convergence. You prove that you can exchange the multiplication and the limit process, and this is actually simple. Well, it's a bit of work, but it's a compactness argument based on some Lyons Aubin compactness theorem. Okay, now the thing is we have to identify the limit as k tends to infinity. Now let me recall that this function f and this function g, if I take the difference, I will satisfy the heat equation. This will also be maintained in the limit as k tends to infinity. Yeah? There's some uniformity which you have to prove, but that's okay. Okay, so here is the theorem. Ignore this for a moment, please, and let me get to the theorem. Now, in full generality, for every nice initial datum for the Boltzmann model, what you prove is that the limit of the solution of the limiting density of Byers can be constructed from a solution of the heat equation phi by just doing this transformation. And this, of course, reminds you of the back transformation in the previous model that I've shown you when you pass from heat to Lazare-Lyons. The density of the limiting density of Wenders analogously. Okay, so basically what this tells you is give me the initial data for f and g. Okay, I will write down an initial datum for the heat equation for you. I will solve the heat equation once and for all, and I will reconstruct the limit from the solution of the heat equation. Okay, now the question is, what has that got to do with Lazare-Lyons? And here is where this so-called well-preparedness assumption comes in. If you assume that the support of the density of Byers sits to the left of the support of the density of Wenders, then you prove by simple verification that f infinity minus g infinity really satisfy Lazare-Lyons. Okay, and you can, I mean, when you just look at these at these formulas, you can see the deltas pop up, right? I mean, when you differentiate the positive part where the function hits 0, when you compute the second derivative, you get the delta. Okay, so just to fix issues here, in general, when we take the Boltzmann model, we can pass to the limit in the number of trading events, and we can construct the limit, and then we can prove if the initial data are well prepared, then we can prove that you get Lazare-Lyons. Now, let me comment on this well preparedness. This is, of course, economically sensible, right? I mean, it would be totally stupid if you had, say, buyers who were located over there, because they would be willing to pay a higher price than necessary. And the same with the vendor. So there is some economic reasoning in that you can accept. Okay, so what's the, Henrik, how much, which?
15 minutes.
Okay, 15 minutes. Okay, so the proof is actually quite cute. Let me just give you a sketch of it. So the main thing to prove is that if you consider this difference, capital F in G infinity minus G infinity, then you have to prove that the positive part of it is precisely F infinity. And if you take the difference again and you compute the negative part of it, you have to prove that the negative part of it is capital G infinity. Okay, so which reminds again of a disjoint support property. All right? And the proof is the following. Take xt and take them such that F infinity at that time t and G infinity are continuous. And we can do that. Okay, there's some compactness for that. And this is very important, and that F infinity at that point is positive. And then what we want to prove is that G infinity at that point is 0. Okay? Now, if capital F infinity at that point is positive, there has to exist an index, but I mean, it's a sum of positive terms. Okay? So there has to exist an index L such that small f infinity at that point is positive. Now, by the exclusion of support property, G infinity at that point is 0. Okay? Now, let me recall that I have another heat equation behind the problem, and that's the heat equation for F infinity plus the shifted G infinity. So this satisfies a heat equation, means this function is positive everywhere. Correct? So that means that if I just go back by A in F infinity at that point has to be positive. And consequently, G infinity at that point has to be 0. So I go back iteratively all the way and just repeat the argument, and what you find is that G infinity at that point is 0. Okay? So that basically does the job. Okay, now there's an interesting issue here. If you look at these limits, what you find is that there is absolutely no reason why at time t equals 0, this function here should be equal to the initial datum for f. And there is absolutely no reason why at time t equals 0, this function here should be equal to the given initial datum for g. So what you will have to expect is typically a layer of fast transition at time t equals 0. And here it is, basically you can find information on that initial layer when you introduce 1 over k as a small parameter epsilon, and you pass to that fast timescale. Okay? So when you do that in the Boltzmann-type model, well, these two terms don't change, but now what you get here is diffusion with the order of epsilon, diffusion constant, on the fast timescale. Okay, this of course is very classical. Now the thing is, consider the limit of this problem as epsilon tends to 0, and this is actually pretty easy. You can get all the estimates rather easily, and what you find is that at epsilon tends to 0, you can just drop these terms, and you get this ODE type system. Okay. Now what you want to know is, when does this system describe what happens what happens close to time t equals 0? Okay. And unfortunately, it doesn't do it for all initial data. Again, there is a theorem which says, and I don't want to go through the technicalities, which says that if you have certain assumptions on the initial data, which are, when you look at it in detail, which are, you could also say, economically sensible, then really the initial layer problem that I've shown you describes what is going on close to t equals 0. That means, in particular, if you take the solutions of the initial layer problem, you let the fast time scale pass to infinity, you will get precisely the initial datum of what we computed on the slow time scale. And the same here. But again, this is unfortunately not universal, but there is a reason why it's actually not. Let me just tell you briefly. Consider this function. Clearly this function again satisfies a heat equation. Okay? Now, as a solution of the heat equation with an L1 initial datum, it will tend to 0 as tau, the fast time scale, converges to infinity. So since both of them are positive, both of them will tend to 0. Okay? Now, actually, I mean, you can find an estimate, and you see, actually, this is sharp, clearly, and what you see here is that what is important is epsilon times tau. So the limits as tau converges to infinity and as epsilon tends to 0 do not commute. So that means the initial layer problem does not, in all generality, provide well-prepared initial data. Okay, so that's, yeah. And the reason, but in reality, what happens is diffusion helps. Okay, even the small order epsilon diffusion helps and does the job. So here, for example, you see a numerical simulation where we did precisely the stupid thing. So you would have the density of vendors initially sit here. You would have the density of buyers initially sit here. So I mean, this would be a totally messed up market, right? Because people would like to pay too much and they would like to sell for too low prices and everything. But then after actually some time, you see everything's, I mean, the problem sorts it out, and what you get is that the density of buyers again sits to the left of the density of vendors. Okay, so there is just one more limit that I want to discuss, and that is trading with high frequency. So when you think of internet trading, for example, in internet trading, you pay very, very low transaction rates, maybe even no transaction rate, okay? But it has to go very, very fast. So there's a lot of transactions, and there is almost no transaction rate that you have to pay. Now, so far, the limit that we have considered is a fixed transaction rate, say order 1, and a large number of trading events. So that clearly doesn't cover this particular case of internet trading. Now, if we want to sort of go into that, we would have to consider a scaling limit where the number of trading events tends to infinity and where the transaction rate tends to 0 simultaneously. Clearly, when you have a two-parameter game, you have to sort of relate the two parameters in one way or the other. And what we do here to start with is let me assume that k times a is a constant. Okay? So if k times a is a constant, you can rewrite the Boltzmann system in this way. So what you get here is this difference, this divided difference appear here. You can pass to the limit in that, and then clearly this divided difference, and you can prove this actually, will converge to a convection term. So what you get is a system of convection diffusion equations, and again there is no, I mean, you see there is no free boundary inside here, right? So let me, on the contrary, let me go back to Lazare-Lyons. So this is Lazare-Lyons. There's only one parameter left, that is a, okay, because k tended already to infinity. Now, of course, I can ask myself the question, what happens as a tends to 0 in Lazare-Lyons? Now, clearly, if I do it formally, this right-hand side annihilates, and I get the heat equation. But that's not the true story, okay? Namely, you can actually prove that as a tends to 0, something much more interesting happens in Lazare-Lyons, and that is you can again identify the limit, V0, through a heat equation. And this is the heat equation, and this is the initial datum for the heat equation. And now what you see here is you have those integrals, shifted integrals, difference of. And that's, of course, when you think of the sums that I've shown you, there was a, the shift was by a. So, I mean, those sums, they can be thought of as Riemann sums for this problem. And actually what happens is you can prove that the limit of Lazare-Lyons as a tends to 0 can be computed from this solution of the heat equation by just taking the absolute value of it, its derivative with a minus sign. And then you can then identify the positive part and the negative part. Now let me compare this to what we previously had. And in particular, what you realize is that essentially through the Hopf lemma, what you show is that the limit, when you move to the free boundary from the left in the limiting solution, and when you move to the free boundary from the right, from the limiting free boundary to the right, is different. Okay, so so in the Lazare-Lyons model, what you have is a layer of fast transition as a tends to 0. Okay. So these limits do not commute, but maybe we can make them commute by doing something different, by playing with the scales, and that's actually what we've done here. Now, for the sake of simplicity, let me now put everything on a bounded domain. That's not important, but it just makes life simpler. And let me consider k times a equal to z to be large. So what would that mean? That would mean that you have a large number of trading events compared to how small the transaction cost is. All right, if you want to look at it in those terms. All right. So then the system looks like, the Boltzmann system looks like this. So you have a 1 over epsilon multiply the convection terms, the nonlinear convection term, and this is actually a rather simple and manageable problem. What you see is that the good change of variables is f plus g and f minus g. F plus g, of course, satisfies the heat equation. So that means once and for all, you can solve this equation. You can find h as a function of x and t, and you plug it in here. Now, what is this equation that you're left with here? This looks like almost like it is a viscous burger on the fast time scale. Okay, so this is really what you want to know. What does viscous burger do on the fast time scale? And I'm not going to bore you with the analysis. There's just one. Maybe I'm going to bore you with the analysis. There's just one cute estimate. When you compute the first order moment of the solution, and you compute its time, and you compute the first order moment and its time derivative, what you see is that this term here pops up. And this can actually, and then you integrate this equation with respect to time, and basically what you prove is that this integral here, keep in mind h is known, h is a solution of the heat equation, and you want to estimate v. Okay, so then this integral here becomes order epsilon. And actually you prove that that absolute v, you could also prove that absolute v is less or equal than absolute h, so that means that v square converges to h square as epsilon tends to 0. That means absolute v converges to absolute h, and you have to worry about the jumps. But clearly, when you talk about burgers, there is an entropy condition, and and the entropy condition here can be expressed by an upper bound, a uniform in epsilon upper bound on the derivative of the solution v. Okay, so basically that means you can only jump down and you can never jump up. So you jump down from h to minus h, and you can never jump up. So that means you can only have one jump, essentially. And so that means you have identified the limiting solution. It is equal to the function h to the left of the free boundary. It is equal to minus h to the right of the free boundary, and what you're left with is identifying the free boundary. But you still have conservation laws, which do the job. Okay, and here is the theorem, and the theorem says that as epsilon tends to 0, there is a unique limiting function v, which is equal to, as I said, h to the left of the free boundary minus h to the right of the free boundary, and you can determine p of t, the free boundary, uniquely through the conservation of masses property. And as I said, h is a solution of the heat equation, which you compute once and for all. So what does that mean in a nutshell? That means that if you start out from the mesoscopic Boltzmann model, if you take the limit as the number of trading events tends to infinity, you find Lazare-Lyons. If you start with the Boltzmann model and you let k times a tend to infinity, when k tends to infinity and a tends to 0, then you get the same thing as the limit of the Lazare-Lyons model as a tends to 0. So this is the way that you have to look at the commuting diagram, sort of. All right. There's one interesting, simple aspect of it, and that is what economists are, of course, interested in is what happens. Does the market stabilize? What do you get sort of in the long time limit in terms of the price? And there is a very simple argument that basically shows that the price converges to its limit exponentially. Okay, and again, this is because the price satisfies a differential equation where this nonlinearity is just given by a known solution of the heat equation. Okay, so let me skip. This is just a comparison, a numerical comparison This is the solution at time t equal 1. So what we have here is a very, very large number of trading events, and you see that Lazary-Lyons and the Boltzmann model, they agree really very, very well, and the same thing over there for the, so yeah, this is the free boundary, and this is f minus g. Okay, here is another interesting computation. Again, what we did is we used stupid initial data. So here you would have one hump for the density of buyers, you would have another one, but in the middle you squeeze the vendors at time t equals 0. And you want to see whether it gets sorted, yeah? In a reasonable economic sense, and actually it does. So you see when time advances, the buyers will always sit to the right of the vendors. So that sort of makes it feasible. Okay, now just to conclude, so what have we done? We have presented a Boltzmann-type price formation model, which was clearly inspired by what Lazary-Lyons wrote down. We showed that solutions of the Boltzmann model converge to the solution of the Lazary-Lyons model when the trading event number tends to infinity, and then we have identified the limits for high trading frequencies, which sort of you can think of as interesting as an application for internet trading. Now clearly there's a lot more work to be done in this, particularly when you think of economically feasible and reasonable model, because the model as it is, if you show it to an economist, he would probably fringe, right? And he wouldn't really like it. But one thing that, for example, could be done is you can work on the collision kernel. Keep in mind that we have really used a very, very simple model for the collision kernel, and you can make that more realistic. Okay. Clearly, another way to go about is why do you have to pay a fixed transaction rate independent of the price you pay? If you think of taxing, it's always percent off, right? So you can think in those terms. Another thing that you can do, which is very fashionable now in economic modeling, is not use a Brownian model for the diffusion, which gives the diffusion, but a more general noise model, like a jump process or something like that. Okay, so yeah, this is all I wanted to say. Thanks.
Is there a relation with a kind of parabolic segregation model in here?
I think, yeah, it is basically a segregation. I mean, with Luis, we have tried to sort of understand the connection with what he did with Van Wallin on the elliptic case, yeah? And clearly there is something like that. I mean, you can see the segregation in the last pictures that I've shown you. But I don't know how to write this in a sort of more general context.
You've done an asymptotic expansion in epsilon.
Have I done an expansion, John? I didn't see it.
Well, you did epsilon go to 0.
That is correct.
But epsilon involved transaction costs and trading rates, so
Right.
it's dimensional. So how do you?
Well, okay.
Can you put that in?
Well, I mean, you know perfectly well that the first thing you have to do to any kind of model is to do a dimensional
Well, when you
scaling.
have you done that?
Yes, we've done that.
Or can you tell us what the physical interpretation is in terms of real trading?
Well, there is, yeah. I mean, we have compared it actually to internet trading. I don't. So we have real data, and I can tell you now the precise numbers. But
what sort of epsilons came out?
Is something like 10 to the minus 4, 10 to the minus 5. And there is, of course, I mean, it's an interesting question in the sense of because there is a whole different range of internet trading systems around. And I think what Marie computed was sort of a range from 10 to the minus 2 to 10 to the minus 8 even. But again, I would not recommend this, and I would not advertise this as an economically feasible model. It was a very interesting mathematical exercise. But if you want to make it economically feasible, you have to go a long way from there.
But still, epsilon small is economically realistic.
Yes, it is. But yeah, there's one interesting, I think interesting thing that we are doing now is, in this model, the market is fixed, right? So there's a fixed number of players and a fixed number of vendors for all times. That's also not always the case over reasonably, I mean, that's almost never the case over reasonably long time intervals because people leave the market and come into the market, right? So what we are thinking of now is modifying the model in the sense of that you think of one time step with a given number of buyers and vendors, then perturb that number randomly at the end of the time step, restart another one. And then actually it turns out that in the limit what we get is a very interesting and even less standard free boundary problem. But yeah, we haven't. And my finance math friend Josef Deichmann says that he hopes that we can see the emergence of volatility through this model. I don't.
Yes, if you have a time-dependent market structure, you should be able to derive Black-Scholes equations.
Yeah, that would be the idea of it. Yes, yeah. I mean, there is, of course, a heat equation already built in, right? So yeah.
Hard part.
That's the hard part, exactly. Yeah.
Okay, with that, this an end to this talk, and there will be 2 focus sessions, following one here and one in seminar 2, starting in 3 minutes. And thanks to and Matteo for the